Welcome back. So we want to continue this morning talking about the few things we left over, or the one thing we left over yesterday about premix combustion, and then we want to move on to laminar premix flames, laminar non-premix flames. So we talked yesterday about the two things I want to point out. We talked about the analysis of the three-step or the two-step really model and the asymptotic structure that results from this, and then also an analytic form of the burning velocity. And it is quite revealing. There are a lot of things that are interesting here. This was from the that are interesting here. You see, for example, how this burning velocity depends here on the fuel mass fraction is linear. You see how it depends on the inner layer temperature. There's a lot of stuff hidden here in these rates and equilibrium constants. And then this is interesting. It depends on this temperature here, or this Zeldovich number to the fourth power, which is the adiabatic flame temperature minus the inner layer temperature to the fourth power. And because at high activation energy, we said yesterday that difference is very small, actually. You can imagine that now when you change the fuel mass fraction, I said it's linear in the fuel mass fraction. That is right. I mean, that's the way you see it here. But at the same time, what happens if you change the fuel mass fraction? If you change the fuel mass fraction, if you lower the fuel mass fraction in a lean flame, then it gets even leaner, or maybe just more diluted at the same, if you keep the equivalence ratio the same. But the adiabatic flame temperature goes down. Okay? So, I think there's a little feedback. Yeah. So, if you make the mixture a little leaner, or you decrease the fuel mass fraction, then you get a linear change here in SL. Or it's not linear, SL squared is linear. But that's a smaller part, really. What happens here is that TB goes down, and because this is small anyways, because of this you get a very strong change. Okay, you might get a very strong change in the burning velocity because of that. Okay, so that's one thing to learn from this, is that, and you see this goes here, this is small, so if you change this by a bit, you change the difference by a lot. And this goes with the fourth power of this. Okay, so keep that in mind. The adiabatic flame temperature has a very, very strong effect on the burning velocity. Okay, that's something, sometimes we don't think about. We think the unburned temperature has a strong influence. Of course, the unburned temperature, it adds to the adiabatic flame temperature, but really, the unburned temperature here, this is a large difference anyways. This doesn't change very much. But this year, it would change a lot. So that's one of the things to take away from this. And then last time we looked at, we said, okay, if we want to come up with a fit for the burning velocities, then having the right basis function for a fit, that would give us a very accurate fit. But now we have an analytic solution that was derived with some assumptions, but it's an analytic solution. And that analytic solution, that gives us an idea how a basis function should look like. And so, we do something like this. Pressure here is an exponential of temperature, which is what all these K's here say, really. And then we keep this form here to the nth power, and so on. We keep the T naught here explicitly in the fit function. And so this here just has a few constants. These need to be fitted to some either experimental data or to other data. And then you get these, you get all these numbers here in the fit, and now you can use this table for all these fuels and use it in a CFD calculation. Or you have a different fuel that you're interested in, you could just use the same fit function and then determine these values and then use it in the code. Okay, so that is that, and then we said we want to talk here at the end briefly about flammability limits, and the reason why I repeated what we did last time because related to this also. So lean and rich flammability limits are a function of pressure and temperature. Lean and rich flammability limits are basically what happens. You have a flame, it moves. If you make it lean, it moves slower, and at some point the flame goes out, or it doesn't move at all. And remember, the thermal flame theory would tell us it would get slower, but there's no reason why it should really stop. And there is a reason. We'll see that later on. But this here is from experiments, and what you see here is, so this is the temperature, unburned temperature for this premixed flame. This is 1 over the equivalence ratio. So this here is rich on this side and this lean on this side. And especially lean flammability limits are of concern. Why? Because the flammability limit is important because you might have a leak. You might have a fuel storage, maybe a natural gas tank. There might be a leak, and then you have fuel coming out, or maybe you have a gas stove at home. You have fuel coming out, and then the kitchen or whatever, you add fuel to it. It gets richer, and then there's some point where it would start to burn. Okay, so the lean flammability limit, usually the one that is of more concern. Interesting here is this is hydrogen, this is methane, and you see methane, hydrogen burns at much leaner conditions than methane, and that's why hydrogen is dangerous. Imagine you have this in your car. People talk about using hydrogen in a car. You have a tank. Then, if you have a very small leak and you get very small relatively small concentrations of hydrogen, it forms a flammable mixture. So there's pressure here. What you see is if you increase the temperature, then you can make the flammability limit goes to leaner regions. That makes intuitive sense. When the temperature is higher, you can burn leaner mixtures. Okay, so let's see if we can explain this. We talked about the inner layer temperature here, and we had this. Now we can just use it to look at this fit function, just to give us a clue what's happening here. And what you see here, so this is basically the same functional form as the result from the analytic solution. And what you see here is that you have this TB minus T naught. And as I said earlier, if you change your unburned gas composition, you change TB also, the adiabatic flame temperature. You make things more lean, adiabatic flame temperature is lower. And so here at the end of the day, you might reach a point where TB is equal to T naught. And then you see from this formula that SLN would be 0. So we can identify TB minus T naught. We can identify this with the lean flammability limit. And you see that if you consider multi-step chemical kinetics, then there is a kinetically determined point where combustion cannot happen anymore. Okay. So now we can look at what determines these values, TB and T naught. T naught in this, you see in this fit formula here at least, T naught here is independent of the temperature, of the unburned temperature, and it also of the fuel mass fraction. It only depends on the pressure. So a given pressure gives you a given T naught. Okay, that's okay. And then the only thing that varies here is the adiabatic flame temperature. So then the adiabatic, the TB then can be determined here from the coupling function again. We have the coupling function. I put the wrong one. No, did I put the wrong one here? No. So we said, okay, so this is the coupling function. written now for this point where you would just get extinction, okay? At this point where you would just get extinction, you have on the left-hand side, you have Y fuel unburned at the lean limit minus Y fuel burned. And so because at the lean limit, the fuel should be all consumed, so this is 0. And then on the right-hand side, you have here this, we said TB should be equal to T naught. And so T naught minus TU and this, okay? And so if I write the same relation here for stoichiometric conditions and divide this here by the rates at stoichiometric conditions, by the value at stoichiometric conditions, I get this. And then you see here, this gives you now an analytic expression for the lean flammability limit. T naught, TU, T stoichiometric, so this is the adiabatic flame temperature at stoichiometric. These can all be determined. Y fuel stoichiometric also can be determined. And so you get, for example, here methane air flame at these conditions. This is adiabatic flame temperature. This is T naught. And then you get a value here for this. And so this corresponds, lambda here is, again, I mentioned this, a lot of this comes from the German version of the slides. And in Germany, for whatever reason, they don't use equivalence ratio. They use 1/, equivalence ratio. They call it the air-fuel ratio. And so that's also why this diagram here was in 1/, equivalence ratio. So anyways, take 1/, this, so roughly 0.5, okay? So that's the upper value. That's an upper value now, an upper limit for the flammability limit, because there might be other things. So here we just looked at this kinetic effect, and there might be other things that also make the flame burn slower. So we can compare this with experiments. These are experiments here for lean flammability limits for methane. So this is the mole fraction of methane at the lean flammability limit as function of the unburned temperature. And then this is the experimental data, and this is the curve that we just obtained. And so you see it's a little lower. This is the curve for SL equal to 0. You might say maybe the flame stops burning at SL equal to 5 centimeters per second. And so if you do the same thing here for 2.5 centimeters per second or 5, then you see actually the trend is observed here very well. And then also quantitatively, this seems to be okay. So something between 2.5 and 10, that's maybe where the flame stops burning. So what other effects could be important for this? So again, the thermal flame theory would not give you a flammability limit, because you see here, TB can get smaller if you make it more lean, but that just means SL gets exponentially slower. But also here, you could imagine that it's not just kinetics that make the flame go out. Also, when you have a flame that burns very, very slowly, then heat losses due to radiation also become important. So you can imagine a flame burns so slowly, has heat losses through radiation, and it just goes out because of the cooling effect. And so if you consider this here, also here you would get a flammability limit. But also that explains why this might be lower than this actual value. Okay? So we talked in this lecture about, so the previous lecture we talked about the kinematics of a flame. Here we talked about the structure. First, the thermal flame theory, where we just have a one-step global reaction. We said there's no competition of radicals, so it's not the full truth. But there's some things that you can learn from this already. But then we looked at the analysis here, asymptotic analysis of the methane air flame based on the 4-step, 3-step, and 2-step mechanism that considers the radicals and the competition. The competition of the radicals, we said, gives you the competition of chain branching and chain breaking, gives you this inner layer temperature. It gives you a condition for a temperature that you have to reach to burn, or under which extinction will occur. And that then explains some of these trends that you see in the burning velocities, but it also can explain the flammability limits. Okay? So, any questions about this before we move on to the non-premix flames? Good. So, okay, so moving on to the non-premix flames, I mentioned this already. Non-premix flames are a lot simpler than premix flames. Sometimes it doesn't seem so because a premix flame just, you know, it just, you just have basically a front that moves from here to there. But determining how fast that front really burns is a lot harder. Also for turbulent combustion, is a lot harder than the fusion flame. So this is a little shorter here. We start out by just talking a little bit about how these flames look like. And then, just like for the premix flames, we looked at some typical, generic, experimental setups that we use to study these flames. We'll do this here also. And then we talk about the flamelet structure, flamelet equations. And then here at the end, I want to, because as I mentioned before, Professor Law asked me to put more CFD, so I want to put in some CFD of laminar flames. I'll show you how you can compute all these things that we discussed so far. And then I have a section here on single droplet combustion. There's one interesting aspect of this, but I decided to skip this because Professor Wrights, in his session, he talks about single droplet combustion and also about multi-phase combustion anyways. So I'll skip this, but the slides are here, and they're, I think they're easy to understand. So if you're interested in this, just go through the slides, and maybe I'll just mention what the key points are. Okay, so diffusion flames, this is of course not a laminar flame, but diffusion flames in general, we said there's premix combustion, there's non-premix combustion, there's everything in between also, but why would you use one or the other? Premix combustion, we said, is very high heat release per unit volume, so you can make things small in a sense. Is a little more dangerous. Non-premix combustion is used, when you don't want to have a premixed fuel-air system that could explode or whatever, and then also often when you want to burn liquid fuels. So this here is an example of a spray injection in a diesel engine. This is an experiment we do in Aachen. So you have an injector here, and then you have the liquid fuel coming out here, and then see the fuel evaporates, and it starts mixing with the air. And then all of a sudden you see here the ignition point, and you see how burning takes place. So this here is just a kind of a shadow or Schlieren image, and you just see the flame liftoff here, for example, is roughly here. So diesel engine, in diesel engines we use non-premix combustion. Why? Because the fuel is supposed to auto-ignite, and so if you would mix it first, then that's actually what you do in HCCI engines. You mix fuel and air first, and then you compress, and then it auto-ignites. But then it's very hard to tell when it will auto-ignite, because if you have a little more exhaust gas recirculation from the previous cycle, the mixture is a little harder, then it will ignite a little earlier, and so on. So it's very hard to control then when it ignites. In a diesel engine, you compress just the air, and when the air is at high pressure, you inject the fuel, and just very, very shortly after that, 1 millisecond typically, or so after that, the fuel will ignite. Okay, so with the injection point, you control when you want to burn. Diesel engine, of course, Professor Wright will also talk about this, but of course, the reason why you compress just the air is because you can compress pure air much, much more than a fuel-air mixture. Fuel-air mixture would ignite much, much earlier, so you have a pure air, you can compress it to very high compression ratio, and then inject and burn, and that high compression ratio gives you a good thermal efficiency. Okay, so in the combustion chamber here, this here, by the way, this is an image I took from using here this exact burner that we have here, and we'll light it up again later on. But so in the combustion chamber, then you have fuel and air mix, and then they, it burns. You have mixing happens through convection and diffusion. What's interesting is that the fuel comes in, and you have the air around it, and even if you have turbulent mixing, the fuel and air, they can burn only really if they are mixed on a molecular level. So on a molecular level, really, they need to diffuse into each other, because otherwise the molecules don't come together. And so you really need to mix on a molecular level. And we see later on that is really an important aspect. Okay, so then typically things burn where you have locally stoichiometric mixture. Why is that? Because it could also burn where the equivalence ratio is just a little lean or just a little rich. Typically, it's stoichiometric conditions, because imagine, let's say it burns everywhere. Then, as we saw earlier, in the rich part there's no oxygen. Okay, the oxygen is all gone, and you just have fuel left over. And in the lean part, you have no fuel, and it's just oxygen left over. And just at stoichiometric conditions, that's where you have your things come together in stoichiometric proportions, and that's where it burns out. So once it burns at stoichiometric conditions, you can't burn in lean conditions anymore, because there's no fuel. And on the rich side, there's no air. So you have the stoichiometric conditions, and then you have the fuel and air diffuse to this point, and come together at exactly stoichiometric conditions, and then being consumed there, and then the products, of course, diffuse away. Simple example here for the fusion flame, of course, the candle flame. You have the solid fuel here vaporizes at the wick, and it vaporizes and diffuses into the surrounding air. Other example of course, is the cigarette lighter, and other example is here my little blowtorch. Okay, so this is how this looks like. You've seen this before. You have the fuel evaporates here. It's very rich here in this part. It's very lean in this part, but then the fuel diffuses outwards. The air diffuses inwards. And you would think at some point the diffusive flux would stop, okay, because everything is mixed out. But combustion always consumes fuel and air exactly at roughly at stoichiometric conditions. And by that, the combustion process keeps the gradient high, okay? So if you have fuel come from here, air come from here, and you just let them mix, then at some point, there are no gradients anymore. But the combustion process itself keeps the gradients high, and that's why things keep going. If you look very closely, if you take your little cigarette lighter, again, I forgot to bring one, but if you take a little cigarette lighter, you should do that, and look at the flame. Oh, you should do this again. I always take this off because there's a little leak. And so I used to have this in my office. And then I fall asleep, and I think, oh, wow, this feels good. And so where's the gentleman here who had here? And so I take this thing off, and nothing comes out. So I need to close this first. I lost my tape here. Okay, so I hold it with my fingers, but I can't do this only for so long because this thing gets really warm. Okay, premixed and non-premixed, okay? So what I want you to see is, if you look very closely to the rim, then you see, where's this? Oh, right, that's very good. Thank you very much. Always keep a little tape. You never, oops, maybe I should go away from that spot. Now, of course, we have some, well, it's not perfect, but so you see we have some, obviously we mix some air. So it's not exactly sealed here. I'll do it again. Okay, so this is better. So what I want you to see is that if you look very closely to the nozzle, you still see the blue color. We said last time this is from chemiluminescence of C2 and OH, things like that. CH, I think, is a little greenish, so that makes it a little light. That's why you get the light color. Then if you go downstream, you see that yellow color, and the yellow color is soot. Soot particles, smoke particles that form here, and they just glow. This is the orange color. And what's interesting is you don't see any smoke coming out here. Okay? You see smoke coming out? No. Also from your candle, typically you don't see smoke coming out. Why is that? Because the smoke is formed and it travels through this flame, and let me go back. You saw the blue color close to the rim. And if you look closely, you see it's a very, very thin sheet. You check this out with a cigarette lighter. You look at your cigarette lighter, it's a very, very thin sheet. And that thin sheet, you see close to the nozzle, and then downstream, you don't see it anymore. So that's the reaction zone. Downstream, you don't see it anymore. It's still there. The only reason why you don't see it in your cigarette lighter is because you have this very, very bright orange color, and so it's so light that you don't see the weak blue light anymore. So the blue light is still here, and it's exactly at this interface that you see here. It's just around this. So this is rich, so you form the smoke, and the smoke is glowing here, and at some point, the smoke has to go through this reaction zone again. Once the smoke hits the reaction zone, which is stoichiometric, then it just burns away, just like the fuel. It just burns away. And that's why you see this very sharp interface. This is exactly where the reaction zone is. Now, you see this flame here is almost opening. If you straighten the wick, then you see sometimes the smoke coming out. Why is the smoke coming out? Because the time for the soot to oxidize is not enough. That's one. So, for example, if you take this thing here and I shake it around, let's see if that works. Now, see this, okay, like this. I did this once in class and I wasn't, you see smoke coming off? Maybe not. I did this once in class and this thing here is not attached. So I was going like this and this thing flows off and flows in the window. It didn't break the glass. But the students were really scared of me from that day on. So if you do this, sometimes there's not enough time. If you do this, you increase the scalar dissipation rate. We'll talk about this later on. You decrease the residence time, and the soot doesn't have enough time, and it comes out. The other alternative is, for example, in your candle flame, try this at home. Take a knife or fork or spoon and just hold it in the flame, and you'll see now there will be smoke coming off. Why? Because putting this thing in, you locally quench the flame, and so this is is like the reaction zone is like a protective force field around this thing. The soot cannot come out without oxidizing, and if you disrupt this here by locally quenching the flame, then the soot can come out this way. And yet another way is, as I said, you straighten out the wick, and then the flame gets longer. If the flame gets longer, then it can open up at the top. And you see this here is almost opening up. Why does it open up? Because you have heat loss. You just have radiative heat losses. You always have radiative heat losses. The radiative heat losses, radiation of soot is very, very strong. So you see this here in the visible, okay, that the radiation in the visible is very strong. But also, if you sit next to a campfire, you sit on the side. Actually, there's nothing flowing towards you, but you still feel it's very, very hot. That's just the radiation from the soot that you get. And so you have heat losses due to radiation of soot. And these heat losses, they can be so strong that the temperature decreases, and then the flame quenches locally here at the tip. Okay? So for example, if you have a big fire, like a campfire, that's the same thing. You see it's very bright at first and gets darker, and then you don't see a flame anymore, and you just see the smoke coming off because you had all these heat losses. Okay, so premix diffusion flame, they are different. Again, we should know this by now, but fuel and air here come from this side. They diffuse into they first heat up, and then they to the inner layer temperature, and then they burn, and so the reaction rate here also keeps the fuel air mass fractions here low, which is why you keep up the gradients and so on, keep this thing going. And the diffusion flame is different. You have the oxidizer come from this side here. In this candle, you have the fuel come from this side, and then they diffuse into each other, and then they meet at this stoichiometric point here, and then they burn, which increases the temperature. And then, of course, here the temperature, again, you have diffusion of thermal energy away from this point, and so you heat up also fuel and air by this diffusion process, and at the same time, you form products here, CO2 and water, let's say, and these also have to diffuse away. And because this whole thing is driven by diffusion, we call non-premix flames also sometimes diffusion flames. Yes?
Well, so it's actually, you mentioned the slide that I was actually going to ask about, but just to clarify, so is the soot and carbon that we're producing, is that, I guess I'd always been under the understanding that was a result of incomplete combustion, but what it sounded like you were saying before in the case of the candle flames, that it's really the result of basically thermal decomposition of the paraffin or whatever before the flame, and then by passing through the flame, the soot is oxidized. So is it, which one is?
Well, essentially it's both the same thing, because in a diffusion flame, that's exactly what you have. You have, if you think of infinitely fast chemistry, then there's no soot. Then you have just fuel and oxygen, they come to the reaction zone, and as soon as the molecules meet, bam, they form CO2 and so on. But multi-step chemistry, real life, the fuel approaches the reaction zone, and it's already very close. And I'll tell you in a minute why it has to be very close. Then it decomposes, like this is what it wants to do, at rich conditions. Even if you don't form soot, that's what the fuel will do. And then it will come closer, these products, maybe ethylene or whatever, they come closer to the reaction zone, and then they start being oxidized with OH and things like that. And then ultimately, it will be CO2. But also there, you could have ethylene leave the flame, unburned hydrocarbons leave the flame because you didn't burn them all out. Okay, that could also happen. Now the soot starts forming from this ethylene or acetylene. You start forming aromatics. These grow further, and so on. And so you can form these particles from this. Now, these particles, again, now this is complicated. We don't talk about soot here in this thing because soot is too complicated. Particles don't diffuse now. This is interesting. Particles do not diffuse because, they're particles. They're not molecules. They're too heavy. Now, what happens is that you form this particle. Let's say here, okay, you form this particle very close to the reaction zone, okay, and then the particles actually, they don't diffuse, but the fuel diffuses, okay? So you have a particle here, it does not diffuse, but the fuel diffuses. So this means relative to the fuel now, you move the particle to the rich region, okay? So that moves again away from the flame. That's good for the particle because it doesn't want to be oxidized, doesn't want to burn its fingers. But then, when you go towards the tip of the flame, it's just that all the fuel disappears. Okay, so at some point, the soot also is pushed into the reaction zone, and then it burns out. And so, if you call this, and if it comes out, that's incomplete combustion. That's correct. But I think what I was saying is just the exact physical mechanism how this happens. Now, I said I promised I would tell you why it has to be very close to the reaction zone. Why does it have to be very close to the reaction zone? Why don't you form soot at very, very rich conditions? Why only close to the reaction zone? You need a little, yeah, that's one thing that people always say. You need a little bit of oxygen to form soot. But why is that? Really, the reason why that is you need radicals. And if you want radicals, we said you get radicals, but by O2 plus H. Okay. If you don't have radicals, things don't happen. You don't. I mean, under rich conditions, you would also form these very large things. But in a flame where you don't have much time, you need radicals, and that's why things happen very close to the reaction zone. So soot is interesting. Soot has an interesting, dangerous life. Soot is a danger seeker because you form soot can only form very, very close to the reaction zone. But if it hits the reaction zone, it's gone. Okay, so soot has an adventurous life. Okay. Good. So we talked about this. We talked about some of these things. One thing that's interesting in diffusion flames, and you see this already if you just look at it. You have different time scales. You have time scale of convection and diffusion. And convection, diffusion, they are roughly on the same time scale. The gradients, usually they don't get as large as for premixed flames. Why don't the gradients don't get as large? The gradients in diffusion flames really are determined by the flow field, not so much by the combustion process itself. And so in premixed flames, we said they're really determined by the combustion process, not by a strain or by an imposed flow field. So the gradients are not as large, so diffusion is not as fast as for the premixed flames, but and then also you have the chemical time scale. Now chemistry is typically very fast. I mean, if things are burning and don't do anything special, it's very fast. And so here you have convection, which is not so fast, and then also diffusion doesn't have that very, very short time scale as in the premixed flame. So what happens here is that diffusion and convection, the flow time scales, they are very slow, and the chemistry time scale is relatively fast. And because of this, in diffusion flames, very, very often, the reaction process, the combustion process, is driven by the slowest process, which now is transport. Okay, so it's not if chemistry is infinitely fast, it doesn't mean you burn infinitely fast because the fuel and the air, they need time to diffuse into the reaction zone. And again, if you look at this thing, you see. I mean, especially when I close these holes, this is very, very lazy. And when I open this thing up here, even if you just get a little, if I open this thing up and I have a premixed flame, you see, things are entirely different. Okay, so one very simple model that you can use for non-premixed combustion is mixed as burnt. Whatever fuel and air mixes, you assume it burns instantaneously, and then you don't need to worry about chemistry or the kinetics or whatever at all. Okay, you could just use mixed as burnt. Burnt, if you say burns to complete conversion, you can just use this Berke-Schumann solution that we had earlier, and it's very simple. Okay, but of course this for the heat release sometimes is actually not so bad. But for other things, it's not so good. So, for example, pollutants, they're formed on slow time scales, and so is not the case. Now, mixture fraction, we introduced this earlier. This is just a summary here again. This would be here a definition of the mixture fraction. Stoichiometric mixture fraction is determined like this, and there's a relation here between mixture fraction and equivalence ratio. A unique relation, and so again, you can think of mixture fraction as just being the local equivalence ratio. You're very rich here at the core of this flame, very lean, or zero actually, in the pure air, and then it's stoichiometric somewhere in between. Okay, so let's talk about some experiments that people do to look at diffusion flames or non-premix combustion. As I said earlier, anytime you want to look at kinetics, it's a good thing to have to do experiments in a configuration that can be computed easily. Okay, and so you want to have a one-dimensional configuration, but that's hard to do so for the premix flame, it was relatively easy. You just have this thing. You have a fuel air mixture, just homogeneous fuel air mixture coming in, and that gives you a flat flame. For non-premix combustion is a little harder, so what people typically use is this what's called a counterflow diffusion flame. So you have two nozzles, one on top, one at the bottom. They have generated flow against each other, and then you have maybe fuel here or fuel in one, and oxidizer in the other one, and then you form a stagnation plane here in between, and then you get the flame here, typically on the lean side of the stagnation plane. And so this is how this thing could look like. This is a design here that we run in our lab, where you have you see you need to do a lot of work here to actually make the flow here homogeneous enough, spatially homogeneous enough, that you don't get local flow effects. So one of the key issues here in a design like this is to create a flow here that has a top hat profile. If you have a profile here like this, then is not good. The following won't work. This is not a 1D configuration. I said earlier we want a 1D configuration, but luckily it turns out that there is a similarity, a one-dimensional similarity solution to this problem. Okay, so we can even though it's a two-dimensional problem, we can compute it in 1D with a similarity solution. And so what I said earlier, if this is not a top hat profile, it turns out that you can't derive a similarity solution, so then it doesn't work. So an experiment is very, very important to ensure this top hat profile, and we spent considerable time measuring velocities here and changing the design to make sure that's what we do. So I want to show you the equations that you solve. These are the equations here. You see there's something cut off here. This is supposed to be a y. V is the velocity in y direction. U is the velocity in x direction. Let's go back, see what the coordinate system is. You see the flow direction, the main flow direction here. The nozzles are in y direction, and the crosswise direction here is x. The radial direction is x. Most people would do this, or some people would think it's more intuitive to go the other way. Does anyone know why? Why typically we use y to go from nozzle to nozzle? It's just interesting. Yeah, but distance from center plane. But that's not the real reason. There's a reason why you use y in that direction. I mean, you could use the distance from center plane. You could use it, call it x. Usually, people would use radial direction is r or y, and the main flow direction is x, right? And here's the opposite.
The flame is in the radial direction, and the immediate coordinate system transforms, so the x corresponds to the radial direction?
X here will correspond to the radial direction, right? But that's not the reason. The reason is this is basically a boundary layer assumption, okay? So a stagnation point flow, you see the stagnation point flow here, this creates something like a boundary layer. So the similarity solution here is very similar to all the similarity solutions you get for a boundary layer, Schlichting's book, boundary layers and stagnation point flows and so on. And in the boundary layer, you have the crosswise coordinate is y. So this is really, for the boundary layer assumption, is really the crosswise coordinate. Anyways, it's not important. I just wanted to realize that the v velocity, that's the velocity that goes from nozzle to nozzle, and u is the one that goes radially out. So this continuity equation here, and you see it's written here for this cylindrical coordinate system, and then this is the x momentum equation, so this would be the radial momentum. Turns out the other one you don't need really. And then this is the energy equation. And so you have your convection in these two convection terms, and then here these two diffusion terms or heat conduction terms, chemical source term, and then this here is the flux of energy by species diffusion, and so on. And so, and this also. And so this is two-dimensional. Now we want to derive the similarity solution. And here I just tell you what the assumptions are. The assumption, first of all, is that you have a similarity solution here for the velocity, which means that you can decouple the solution in x and y. And so the assumption here is that the U field can be written as g of y, so g is just a function of y, not of x, times x, okay? And so you could look at this g as something like a strain rate. So if you look at this could be, if you assume that g is not a function of x, then in x direction you could say the g is du dx, okay? So here u is the u dx times x, okay? So du dx, that would be the strain rate. So you could look at g as something like the local strain rate. This is a typical, again, if you look at Schlichting's boundary layer book, this is a very typical assumption for these stagnation point flows. Stagnation point flows, why is this important? Why is, again, why the boundary layer people, the aerodynamics people, why do they look at stagnation point flows a lot? Because if you have an airfoil, you always have a stagnation point on the tip of the airfoil, and you want to use your boundary layer theory should start right at that point. So that's an important point that the aerodynamicists have looked at a long time ago, and so the combustion people just picked that up. Okay, so so this here is something like the strain rate. This is a similarity assumption. And then the similarity assumption for the pressure here also. You say the pressure is something like a background pressure. This would be the thermodynamic pressure. And then minus P times x squared times F of y. So basically it's the same thing. You say I can decompose the pressure in a part that only depends on y and a part that only depends on x. Okay? So that's the similarity assumption. Turns out this is written in a way, so for those of you who know low Mach number, so all this is in the low Mach number limit. If you look at the low Mach number limit, then for the pressure, typically you derive a Poisson equation. And so this here satisfies the Poisson equation. Okay, that's basically what it does. It's an assumption that you can split these in functions of x and y. And this here is chosen, you could say, is chosen such that it satisfies the Poisson equation. Okay, so the third assumption here is that mass fraction and temperature have no radial dependence close to the center line. So this means basically along these lines here, along the flame here, let's say, the temperature and so on, they are the same, they're constant. Okay, so if you do all this, you plug this in the equations, you see that the x direction here, it drops out, and you see I get a system of equations here only in y. And let's see, so this continuity equation, this here, and you see, I said earlier, you can look at g as something like du dx, and that, that makes sense here in the context of the continuity equation. There's a momentum equation in G, and then, in X direction, and then this here, and this is the temperature equation. And there's one thing here, you see, you have this P prime here. P prime, what was this? P prime was just this coefficient here. Okay? So how do we get the P prime? There's an equation missing, maybe. Because we have we have G, and we have V, and we have these two equations, okay? But now we also have this P prime. How do we get P prime? Okay, let's think differently. What are the boundary conditions now on this? Boundary conditions are, we have, you need to specify on both sides, both nozzles, you need to specify temperature and composition and all these things, but also the velocity. You specify the velocity here and you specify the velocity there. Okay? So I specify for both the v velocity and the g velocity or the u velocity, I specify velocities on both sides. Okay? Is that a problem? And it's obvious, right? I mean, it's obvious that you need to specify both the u and the v component at both nozzles. Is that a problem? Why is it a problem? Because I have these two equations here for u and v, or for u and g, okay? And this is a second order equation. Okay, I can specify two boundary conditions. But this here is a first order equation. Okay, how many boundary conditions can you specify for a first order equation? One, but I have two. What do I do now? We had this yesterday. What happens if you have an eigenvalue? There must be an eigenvalue, okay? There must be an eigenvalue that will have to be determined such that it has the exact magnitude such that the equations are satisfied when you specify all these boundary conditions, okay? So basically, P here is the eigenvalue, and P, again, is specified such that all boundary conditions are satisfied. Okay, so P is an eigenvalue. So this is how you do this. Here the assumption is you have two nozzles. The nozzles, they have a certain distance. You have a certain velocity here on the upper and lower one. Typically you say, or very often you say, the flow is just straight, and so the u component is 0. But as a matter of fact, in real experiments, that's almost never the case. So you do have a change in u, and so here you can specify this du dx gradient also. There's another way of looking at this. This is the historically this is the standard way, and that is to assume this is better for. So this is good for this formulation. Good for experiments. You have an actual experiment, you can match it here with these equations. But for doing just analysis, there's another formulation where you assume the streams come from infinity. Okay, they come from infinity and then they meet right here. And so if the streams come from infinity, far away from the stagnation plane, then you have a potential flow. And so this is the similarity solution here. That assumes a potential flow far away from the stagnation point. This, again, I just want to show you these equations because you'll see these equations, somewhere. And so that you know where it comes from. Here, the u dx, we said earlier, that's basically the u dx is the strain rate. And so the strain rate, du infinity, so this u dx at infinity, that's how we define here the strain rate. We introduce a similarity coordinate. Here it depends on the strain rate. Gives you here a time scale, and this is a mass-weighted coordinate here. Rho dy is just a mass-weighted coordinate. So this is very, very typical for a similarity. If you look at all the exact solutions and for boundary layer flows, they all look like this, basically. That you have a transport coefficient here which has a time scale, and then you have some other parameter here which gives you time scale, typically also this factor 1/2, this 1/2 here is what you get. So then we introduce the stream function. Why do you introduce the stream function? Because that's good for analysis, because if you instead of solving for u and v, you solve for the stream function, then you satisfy the continuity equation exactly just by introducing the stream function, and then you have one equation less. Okay, so for analysis this is good. That's why people do it. So introduce the stream function. U is basically df dy. F is the stream function, and f is defined so that u is df dy and v is minus df dx. Okay, that's typical definition of the stream function. If you take the continuity equation and you plug these two things in, then you'll see that it's identically satisfied. Okay, so there is this Chapman-Rubezine parameter is defined like this. And then if you plug all this in, then this is the system of equations we get. We don't have the continuity equation here. It's satisfied by the stream function. We have this equation here is the momentum equation we had earlier. This is the species equation, this temperature equation. Okay? And so isn't that good? Wouldn't we always solve this rather than the earlier form because this has one equation less? Isn't this much better? Why don't we always do this? Just by introducing stream function now, we have one equation less. And so you solve these here for f, okay? You solve this for f, and then you see down here, so these are the boundary conditions, and then you see down here, once you have f as function of eta, then you can compute u and you compute v. Easy, very easy. No, the stream function you can always define. You can always use stream function. Gives you one equation less. Why don't we always do this? Seems like you get something for free, while there's a saying, there's no free lunch. Okay? So what's wrong here? Where do we need to pay?
You need to take everything out of the similarity coordinate?
No, because if you have the solution to this, then this last step here to compute u and v is trivial. Solving an equation like this is much, much harder than doing this here at the end. This is trivial. Yes?
Some boundary conditions you cannot match sometimes?
No. Boundary conditions here are good. They are, you see df dy here, f equals 0 and so on. This is all straightforward. Boundary conditions is not a problem. Right, then we use the other one, but we could still do this. We could still introduce a stream function and get rid of the continuity equation. It doesn't, pardon?
It doesn't make it always necessarily simpler.
Yeah, why not? You're absolutely right. It's not simpler. But why is it not simpler? Look at the equations. Somebody said second order. What is the deal with the equation here? This is not the problem. Look at this. This is a third order equation, okay? We started out with a second order equation, plus we had the continuity equation. We said we make it simpler. We take out the continuity equation, but again, there's no free lunch. Now we have a third order equation. And as a matter of fact, you know how we solve this when we write it in numerical code? You don't discretize this third order term the way it is. We just introduce a new variable, df d eta. Okay? df d eta is a new variable. Then this equation here will be written in terms of this g, let's call it g, okay? Lowercase g. This will be dg d eta, and this will be, just a normal diffusion term. And here we have one more equation, which is g is equal to df d eta. Okay, so that's how we solve it. So actually we go back when we solve it numerically, but for analysis, this is not bad. So this is why for analysis you always introduce the stream function. When you actually solve it, you take it out again. There are stream function formulations in fluid mechanics, but anyway, so if you solve this now, you can solve this. Then this is what you get. Here we have the temperature profile for 3 different strain rates. So the strain rate now, that is a parameter. There is an independent parameter in this problem. And that's the nice thing of this configuration, is that not only do you have see this in the premix flame, you don't have, in this flat premix flame we had, you don't have this. In the flat premix flame, all you have is let's say the unstretched flame, there's no freedom, there's no free parameter. Here you have a fluid mechanics timescale that you can vary, okay, by varying the velocities of the nozzles. Very high velocities of the nozzles corresponds to very high strain rate, very low velocity of the nozzles, very low strain rate. Of course, again, you vary the velocity of the nozzles, you get high strain rate. Strain rate is the inverse of a time. This means, so higher velocities means you get a higher strain rate, lower residence time, and this, of course, then changes the Damköhler number. Okay, so you go to smaller Damköhler number. Okay, so we look at three different temperature profiles here. So there's one nozzle here, there's the other, it doesn't matter which one's which. And then you see this here is the blue is the very low strain rate. Okay, so see, I didn't even plot the whole thing here. I mean, this goes to all the way to here or something. Okay, so this thing is very, very wide. You increase the strain rate, you blow harder from both sides, you squeeze this thing together, and now you see the gradients become larger. That's what I said earlier. The gradients now, they are not determined by the chemistry anymore, because the chemistry takes place right here, right where the temperature is maximum. That's where the chemistry takes place. That's why the temperature is maximum at that point. And you see the gradient at that point is 0. Temperature gradient in the reaction zone is 0. Okay? So it's very, very different from the premix flame. And then this higher strain rate here, and then even higher strain rate. And you see, this becomes very, very thin now, and the gradients become very, very large. Okay, so the strain rate also, it kind of corresponds also to the local gradients you get. Now you see that you can even plot these three here in one plot. Okay, this here, by the way, is not cut off here. It also, I mean, it's computed up to the point where the gradients are really 0. Okay, but so they're on such different length scales. Now, what happens if we plot this as function of mixture fraction? And then you see they all kind of look very similar. Okay, so that is the power of this variable mixture fraction is that it scales everything to the in diffusion flames to the same scale. And what you see then here is that actually there's little change. There's little change from the very small strain rate to the smaller strain smaller strain rate. I think I made a mistake here. I made a mistake here. So the green curve here, that is here also it's wrong. So the blue is the high temperature. The red is the very high strain rate, and the green is the intermediate strain rate. Okay, so this low strain rate, higher strain rate, yet higher strain rate. And you see from the low to the intermediate strain rate, there's not much change if you look at it as function of mixture fraction. When you go to the very high strain rate, then the temperature actually it changes quite a bit. Oops. What does it say now?
Encountered an error.
I crashed. Oh, did I say don't send, right? Okay, let's do that again. Here we go. Okay, let's see where we are. Okay, so you saw that by changing the strain rate, you change the temperature. Why is that? Because you see immediately, I mean, you go to higher strain rate, you squeeze this thing so much, this flame so much, that the gradients become so large, actually, that you can imagine that you have very strong heat losses from this thing. Because the temperature gradient is very large, you have a very, very high flux of thermal energy away from the maximum temperature. Okay? And so if I plot here just the maximum temperature, or the stoichiometric temperature of each of these flames as function of the strain rate, then you see the temperature keeps going down, 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 and at some point you know, it just goes straight down and the flame extinguishes. Why does this happen? Again, you go from here to here and you squeeze it more. Now first, not much happens. You see the temperature goes down a little bit, but not so much. Why is that? Because now comes the Dampköhler number. Dampköhler number compares the flow timescale with the chemical timescale. If the flow timescale, if the chemical timescale is much, much shorter than the flow timescale, or the chemistry is very, very fast compared to the flow timescales, then you know, it doesn't matter what the flow timescales do. So I squeeze this more, I get more heat losses, but at the same time, the chemistry is infinitely fast anyways. I mean, you can also see that I squeeze this more, I have more heat losses, but at the same time, also the gradients for fuel and oxygen get larger. And so I also bring more reactants to the reaction zone. So you could imagine not much happens. So at the limit of very, very fast chemistry, nothing happens really. But at some point, the Dampköhler number now gets smaller, smaller, smaller. And if I squeeze this even more, now I have a lot of heat losses. At the same time, I have a lot more fuel and oxygen coming in, but they don't have the time to react anymore. Okay? And that's why the temperature here goes down. You still bring all the reactants you need to the reaction zone, but they can't burn anymore. Okay? And that's why the temperature goes down, down, down. And then here you can imagine what happens. You reach something that you know, is in a layer temperature or whatever, and then you get extinction. At some point, it can't burn anymore. Okay, so that's something you see in these counterflow flames. These counterflow flames, they're often used to just determine this extinction limit. And this extinction limit, the strain rate at which you get extinction, that is you could look at it as a kinetic parameter, just like the burning velocity. Okay, is in a sense is a similar parameter, but now for diffusion flames and not for premix flames. Okay, so now we want to talk about the structure of these flames. We said the assumption of fast chemical reactions is... let's go back. Are there any questions about this before we move on? Yes?
You go back to the flame.
This one?
Yeah. The flame position actually shifts from the linear to the center of the, y equals 0.
Yeah.
So why is that? I mean, it only shifts when
Yeah. Yeah, good question. What you see here is that relative to the mixture fraction, the flame position doesn't change. Or it changes a little bit, but not very much. But here, this 0, it has no real meaning, you could say. That's why, so where I put the 0 here is, in a sense, is arbitrary. And so I don't even remember exactly how the 0 point here is chosen. Because what you saw in the boundary conditions here is that we say F is equal to F is the V velocity, which is positive, or let's say negative on the top, positive on the bottom, and it's 0 exactly at the stagnation point. So here you say you put eta equals 0 would be exactly the stagnation point, but that's not how we do it, because that would be an internal boundary condition. So we specify something at the boundary, but I don't remember exactly what it was. So, but this is, in a sense, is arbitrary. You could shift this back and forth. Yeah, that's a good point. So, but in mixture fraction, you see they're all the same. Okay, other question? Yes?
How do we define the strain rate?
How do you define what?
Strain rate. The flow strain rate. How do we define
The strain rate? Yes. The strain rate is, in a sense, it's an arbitrary definition. Because, again, it's just a scaling parameter. Here we just say, I mean, there is a definition of the strain rate in fluid mechanics. But for our purposes here, it doesn't matter how we define it. So you could, for example, say the strain rate is the velocity from the top minus the velocity from the bottom divided by the distance. That's one measure of the strain rate. Here we say it's du dx at infinity. Du dx is minus dv dy by continuity, dv dy dV dy, that's again the same thing. dV dy, the average dV dy is the what do you call it? The difference of the velocities divided by the distance of the nozzles, let's say. But here we don't have a nozzle. This is why, this is at infinity. But the point is really, this definition, it never really comes in at the end of the day. I mean, at the end of the day, you just have this value. Here, it's just important that you define it the same way, if you want to define it. But you see, when you compute this flow using this set of equations, which describes something that has actual nozzles, there is no strain rate here. Okay? Basically, the P parameter here, that's a measure for the strain rate again. You can actually relate that back to the strain rate, or you can define a strain rate from this. What's more important here is that when you compare with an experiment, that you use the same strain rate, the same definition of the strain rate. That's the most important thing. Exactly how you do it doesn't matter too much, but you have to keep in mind, you have to do it in the exact same way.
How experimentally we change the strain rate to calculate the extinction?
Pardon?
How experimentally we fix the strain rate? Experimentally.
Again, experimentally what you fix is not the strain rate. What you fix is the velocities. You fix mass flow rates in an experiment, right? Mass flow rates, diameter of the nozzle, whatever, that gives you velocity. Now, typically what people do when they run an experiment like this, where you try to find the extinction point, you increase the flow velocities and you keep the momentum balance. The momentum from top and bottom, you always keep that the same. So you always increase both at the same time. There's one way to do it. You could do it differently, but let's say that's how you do it. And then again, you just define a strain rate, and how you do this is not so important. You just have to say how you did it. So again, you could take the velocity from the top minus the velocity from the bottom divided by the distance of the nozzles. That's one way to do it. And some people take the velocity gradient at some point. But that, of course, from an experiment is hard to measure. But that would be one way to do it also. Okay? It just the important point is that you say, as when you did an experiment, how you actually did it. Okay? Other questions? No? Okay. So let's see. So next thing we want to talk about the flame structure. We saw that it is a good thing to look at these diffusion flames as function of mixture fraction, and we will actually develop solutions to the governing equations as function of mixture fraction, and that is the so-called that is given in the so-called flamelet equations. So we said earlier, assumption of fast chemistry is sometimes good, but we just saw, if the flow timescale is small enough, the velocities are large enough, or the strain is large enough, then of course this assumption of infinitely fast reaction is not true. Also, if you for certain processes in combustion, is the infinitely fast chemistry assumption is not true. For example, you look at liftoff. If a flame is lifted off, it just means it wasn't fast enough to burn very close to the nozzle. Extinction, is something that signifies finite rate chemistry. Pollutants, I mentioned this earlier. Oh, I didn't actually say this earlier. I talked about the oxidation of the soot, and you see how really fast this is, but because you have this very, very sharp interface between the sooting region and non-sooting region, which basically means the oxidation is very fast. When we look at how soot is formed, it's actually very slow. You see close to the nozzle, there's no soot, and then you see it slowly forming when you go downstream. So formation of pollutants, also NOx, that is a very slow process, and infinite fast chemistry assumption is not justified. So in the flamelet formulation for non-previous combustion, what we do is we introduce, instead of looking at a flame structure as function of physical space, and you saw, that is not a good idea, we look at the flame structure as function of the mixture fraction. So we introduce the mixture fraction as an independent coordinate, replacing one of the spatial coordinates. And then, this leads to a system of equations, which is still quite complicated. And then we can do, again, we use asymptotic approximations, and then we get to one-dimensional equations that describe what happens, the structure of the reaction zones, and they're actually fairly simple equations. And also, they can tell us a lot about the physics of the of non-premixed flames. So maybe, when was the break? Was 15 minutes ago, right? Oh, sorry about this. I thought the break is at 10. So let's break for 10 minutes then. Let's meet again at 11 minutes past 10.